At Curio, we believe that the future is nuclear and that the future of nuclear is a circular economy. Now, recycling spent nuclear fuel is a rich topic with a lot of intimate details about it. I'm only going to scratch the surface here, but hopefully I can get you guys excited like we are. So first, a little bit of an introduction to our company. A lot of people call us a nuclear recycling startup. While that is true, we focus mainly on nuclear recycling. Nuclear recycling opens up a wealth of opportunities that we want to explore and bring to the future. So we view ourselves more as a nuclear innovation technology company. I was taking an Uber here, and I was talking to the Uber driver, and I mentioned I came here to present on recycling spent nuclear fuel. And he said, "Oh yeah, that's a big problem, nuclear waste." And I said, "Do you know anything about it?" And he says, "No, but I do know that it is a problem." And fair enough. Right now in the US, we have something close to 90,000 metric tons of nuclear waste. It is sitting across 81 sites. All of that was supposed to go to Yucca Mountain. We have a nuclear waste fund that we collected money for. That's about $50 billion it's up to now. That is not going to be enough to pay for it based off current estimates. And Yucca Mountain is just not happening anymore. So what do we do instead? We have it sitting on site, and we're paying about $1 billion a year to store it on site. Now, if you look at the fuel itself, 96% of the energy potential is still in there. About 95% of the spent nuclear fuel is uranium, and we want to recycle that. So what you do is you build a facility that could recycle that. So we're making about 2,000 metric tons of spent nuclear fuel a year. We want to construct a facility that will process 4,000 metric tons in a year. Now, at that level, you'll be able to produce enough uranium to power about 40% of the reactors now. And if you use the transuranic product, turn that into advanced fuel, you could power roughly an equal amount of advanced reactors for that. Now, we want to go on this at a more economic approach. Currently, other countries recycle, but they see that more as a task that the government needs to do. We want to approach this from an economic perspective. We want to recycle, and not just for it to cost money, but to make money doing it. And by doing that, we focus on trying to extract as many products as possible. So we're eyeing something over 10 products that we want to extract out of the spent nuclear fuel to sell into the markets. And in doing so, we plan on reducing the waste volume by 96%. So we think this is possible by using our key technology, NuCycle. NuCycle is what you see here. It's kind of a cartoon version of it, but it focuses on 3 different unit processes. The first one being decladding via oxidation. Now this is where we can take the product, the fuel, spent fuel rods as is, put them into our facility in the first unit process, and it will open that up and turn the product into a nice mixture that we can work with. Then we take that to fluorination. We're looking at selective fluorination. And where this is exciting is you can take the uranium out as UF6, and if you look at the front end of the fuel cycle, we turn uranium into UF6 before we put it into enrichment facilities. So this can go straight back into the front of the fuel cycle, how we use it now. And then at the last bit, we're going to use electrolysis to extract out the remainder of the products. And this is where you'll get out your plutonium and your other minor actinides. You'll get those in a commingled state we call true fuel. So when developing our technology, we had a series of goals that we wanted to achieve. So in the first unit vessel, we wanted to split open those rods and turn the spent nuclear fuel into this small powder that would really react with our fluorinating agent. We want to really reduce the amount of spent nuclear fuel that is left on those cladding hulls. And a lot of the cladding hulls, particularly the zirconium one, we also want to recycle that and put that back into the fuel cycle. Now, this is also the first point where we'll get out key isotopes. One is krypton-85. Right now, we regulate that. We don't want that to be emitted, but we also use it. We use it primarily for leak testing. It is a great material that you can use to test for leaks. We use that in the defense industry. And right now, Russia has a virtual monopoly on it. And in recent years, we kind of found out that it's probably not a good idea to rely on Russia for key isotopes that we use in defense. But there's other isotopes we want to get out. We want to get out tritium. Iodine is not really used for anything, but is a problem with disposing spent nuclear fuel. Want to get that out there. Xenon is important for space travel, things like that, and we want to get that out at this point as well. The next step is fluorination. Now we're looking at a temperature-based selectivity with fluorination. Right now we are focusing on a unique fluorinating agent that at lower temperatures, it takes out those nasty fission products that will fluorinate. And as you raise up the temperature, it will start to react with uranium. So you can take that uranium out in a near pure form that you can do very little processing to it after and then just put it straight back into the fuel cycle. And right now, it looks like plutonium, with our fluorinating agent, plutonium will never fluorinate. It will never turn into a gas and it will never come out at that point. So that will stay in with the other minor actinides and with some of the fission products. So that's definitely a safety and security standpoint that is very valuable. Now for the remaining product, we want to co-extract that out as true fuel. True fuel is a unique product that I'm going to talk a little bit more about, and that will be great for advanced reactors. But there's not just true fuel there. There's also a lot of precious metals. One thing we're looking at is platinum metals. You can get a lot of those out at this point. And two isotopes that we are looking at this point, trying to extract, is strontium and cesium-137. So strontium-90 and cesium-137, these two produce something around 80% of the heat in their spent nuclear fuel. And that's one of the main limiting factors when it comes to disposing your spent nuclear fuel. But for something like strontium, there are companies out there like Nano Diamond Batteries that want to use this and turn this into, take the heat, the radiation from it, and just turn that straight into energy. They're looking at making these small batteries that will last years and years. So if we can take that, that's a huge problem for disposing this, and then just turn that into a product that you could use in the economy. That would be great for us. So we have these ambitious goals. We took them to some of the national labs here, and luckily we got 4 of them to say that they are enthusiastic. They have time and ability to help us develop this. So up here we have sort of an organization of those labs. We have Idaho National Lab, Pacific Northwest National Lab, Oak Ridge, and Sandia National Labs. We also have Spectrotech, that's an early engineering partner. And together we came up with a research program that we pitched to ARPA-E. And this is to do some of the early proof of concept work for this. So luckily they accepted that. We got our ARPA-E project funded. They were focused on the first 2 unit vessels. The 3rd unit vessel, we ended up getting a GAIN voucher to explore that. But right now we have Oak Ridge, who is doing the first unit process, Pacific Northwest National Lab doing the 2nd unit process, and there we have Bruce McNamara, who originally found this temperature selectivity. So it's great to have him on board. And then we have a full integrated demo that's going to be produced at Idaho National Lab. Now, right now we're working on simulant material, and we've already shown pretty good separation with the simulant material. We got pretty pure UF6. out of that. And at the end of this year, early next year, that's when we're going to start doing these tests with actual spent nuclear fuel and just see what that looks like in a radiation environment. And then Sandia National Labs, they're going to take some of this early data that we get out and use that to help us construct safeguards by design for our facilities so we can keep this secure and safe. Now, what does this mean in terms of waste if we are successful? Well, this means a dramatic reduction in the volume of waste that's going out. Right now, you can compare this to Purex. This is what is done in other countries like in Russia and in France. And we're looking at an order of magnitude reduction in the high-level waste. So when you have waste volumes this small, you no longer have to focus on these large consolidated facilities like Yucca Mountain. So something like Yucca Mountain, they expect it to cost $90 billion. I think that was back in 2000-something dollars. It's going to be over $100 billion now. We have $50 billion in the spent nuclear waste fund, which, by the way, is already spent. So we have to somehow get that money back up. So when you have these small volumes, you can really open up other opportunities for spent nuclear fuel disposition. So what we seem to favor at our company is deep boreholes. So boreholes, instead of these big facilities, you just have a small hole that is dug very deep, talking miles deep underground, to where even if the packaging breaks, it's not going to get back up to the surface for millions of years. So when you have these huge reduction of volumes, you could actually take all the spent nuclear fuel in the country right now and dispose of that in 4 boreholes. So this conference room right here, that is enough space to dispose of all of the spent nuclear fuel in this country if you reprocess it. So that's a huge deal. That opens up a huge opportunity. Right now, we spent in the nuclear waste fund something like $800 to $1,000 per kilogram to dispose of it. And if you look at some of the prices coming out of La Hague for their reprocessing, that's about $1,600 per kilogram. So that's already too expensive. We want to get something that is much cheaper and then reduces your waste disposal cost as well. Another thing we're looking at is the transuranic product that's come out. We call it True Fuel. Now, this product is going to be different depending on the spent nuclear fuel you get out. But when you get to the volumes that we get to, you can somewhat homogenize that. You can mix batches. You can get some more standardized fuel forms. So right now we're doing some studies of what would this look like in different type of reactors. So up here we have Lightbridge Fuel. They're an innovative advanced fuel design company. They're looking at putting metal fuel in current day light water reactors. That is attractive to us because there are light water reactors right now, so we can actually address that market right away. And we also looked at something like EBR2. That's where a lot of these fast reactor companies, they're basing their design off of EBR2. But when you put True Fuel into these reactors in a thermal system like an LWR, True Fuel is a pretty good replacement for HALEU at that point. You might want to remove the minor actinides at that point for various reasons, such as waste and safety. But in a fast reactor, you can really utilize a lot of this stuff. And there you also get, instead of this 2.5 neutrons per fission, you get something closer to 3 neutrons per fission. So that's a huge deal when it comes to transmutation of products in these fast reactors. So putting True Fuel in a bunch of these other reactor designs are all well and good, but really what you would want to do is you build a reactor that is specialty purpose for this fuel. Our CEO always brings up the metaphor of IBM and Microsoft, where IBM was looking at this as a hardware design, and that was the future. And you'd think that IBM would be the biggest company, 10, 20 years in the future if you're looking at it in the early 90s. But Microsoft was looking at it as software design, and it really took that software, and that really ended up driving the technology. But we want to take the fuel and drive reactor design from that. So we want something that is safer, more economic than what comes out now. We here at Curio are pursuing our own reactor design. We call this the homogeneous plutonium eliminating reactor. We shorten that to HOPE. This will be a molten salt reactor. You have some issues with fuel, like true fuel, that can sustain a fission chain for a very long time. But if you have these solid fuel rods, they degrade over that time, so they can't actually keep up with true fuel. But if you have a liquid fuel, that could really realize the full potential of true fuel. So we have essentially this two-fluid reactor design. Now, one bonus of true fuel is that it's very dense in fissile material. That's typically what you run your reactor off of. So when you have a molten salt, you want it to be at an ideal concentration for hydraulic purposes. But you're now limited at what enrichment you can get your uranium to. But with true fuel, you can have a lot more fissile packed into there, so you can make the reactor design a lot smaller. We're looking at this two-fluid design. You have sort of that central cavity region. That's where the core region is going to be. That's going to be a fast spectrum that is burning this, quote-unquote waste, and instead turning that into cheap, clean energy. And then we have this secondary region, which we're going to fill up with graphite and turn that into a thermalized region. So as a result of this, you get kind of these two spectrums. One neutron spectrum in the reactor, which is characteristic of a fast reactor, but then this secondary neutron flux spectrum in the secondary salt, which is much more thermalized. Now, where there's advantage for a thermalized spectrum is that materials tend to absorb neutrons much more readily at that. So this really increases the transmutation potential. And where that could be a big deal is if you could fill up this blanket with thorium. So once you have a bunch of thorium in there, you can produce a lot of uranium-233. You can take that out of there and put this into a lot of these proposed U-233 thorium fuel cycle designs and start that up just on a thermal spectrum there. And that's where U-233 is really the best, is in a thermal spectrum. But we also get some other advantages. We have our chain reaction is dependent on these thermal neutrons, but they're a lot easier to control. You can use, control rods are much more effective on them. So we can run this reflector control essentially to increase the safety margins of our reactor. So at the end of the day, we're hoping to bring NuCycle into fruition, and with NuCycle, that brings a lot of opportunities in the future, not just with advanced reactors, but with medicine, with industry for other isotopes. And we really hope to foster this community in the future. And really, there's a lot of applications that you can use, not just medical and industrial, but space. That's another one we are also looking at. And I'll be happy to talk to this anytime with anyone after this, but thanks for listening to my presentation.
Shine up in Wisconsin wants to do a little, much less complex version of this, but they want to do a little bit of fuel recycling also. We had the typical usual suspect pants wetters like Ed Lyman and McFarlane wrote a big letter saying how scary and awful and proliferation causing that would be. So, I mean, you don't need to give away your secrets, but like, what do you think your general way to deal with these people who want to block your progress?
Yeah, I predict there'll be a problem. The big issue with Shine is they're looking at something like a Eurex type system. So they're extracting the plutonium with the uranium. And if you looked at their argument, they said that putting uranium in with the plutonium was not a big enough of a barrier in their mind. The standard right now for increasing the barrier is to include fission products with the plutonium. We plan on extracting the plutonium with fission products at that point, so it's a lot safer from that perspective.
Good morning, Ron Medina. I did have a question on the deployment of the NuCycle. So is it like the Yucca Mountain, you have a central facility that these 86 sites would bring their spent nuclear fuel? Or would it be an in situ kind of deployment where these 86 sites would use the NuCycle process and dispose of their fuel?
So right now, we're looking at a central facility that has a lot of economies of scale with it. One of the big issues is security. Talking to the people at Sandia, you have a fence around it that could, your operation costs could be pretty close to 40% that. And when you have these different sites doing it, that can really increase your cost. So we think the most economic approach is going to be a centralized facility, but our design is modular. If you remember that tri-unit vessel, we're going to have 10 of those in a facility. So that could be easily split up into 2 facilities if the economics prove out that way.
Do you have a target date for when y'all would start on commercial?
Yeah, the commercial deployment, we're looking at something from the early to mid 30s. Right now, we are planning the next stage after the ARPA-E project is to go to a pilot facility. We want to do that under DOE authority because that will be a lot easier. We can get the data from that point and just take that to the NRC and say, this is how this process works. This is how it's going to work. This is how it will be safe. The NRC is, of course, a big question mark, but they have their time goals out there, and if they stick to them, it could be more towards the early 2030s, but if they do what they normally do, it will probably be more like the mid-2030s.
Very good. Let's give Alex a hand. Appreciate it. Thank you, sir. Very, very grateful for you.